All right, good afternoon. In the time we have left, we're going to cover the remaining couple of slides on the power sources, voltage as well as current. Let's see. So we had looked at this and we talked about maximum power transfer. Okay. All right, so this is going to go by a little bit quickly. All right, so if you want to find maximum power, let's say we have a source, voltage source Vs with a source resistance of Rs, and we connect a load resistor RL to its output terminals. In order to find the maximum power that is being transferred, we can vary the value for RL from 0 to infinity and determine what point or what value of RL receives the maximum power. So standard equation, power is equal to I squared times R. So PL is I squared L times RL. And IL is the current that's flowing through the circuit. Again, apply Ohm's law. I is equal to V over R. V divided by R. Total R is Rs plus RL. Thus, we get an equation for PL Vs square times RL over Rs plus RL square. Now, we can vary it. Oh, sorry, not there. We rearrange the terms Vs square or Rs square. That gives us, or that should give us, the current I, right? So V square or Rs. And then we set the ratio of the load resistor RL and Rs, and we note it as X. We can vary X from 0 to infinity. If we go to 0, power delivered to the load is 0. If you go to infinity, power delivered to the load is 0. So the max or the minimum value for RL is neither at 0 nor at infinity. Okay. It turns out that maximum power is transferred when the source resistance, when the load resistance matches the source resistance. So RL must equal Rs. And the equation for maximum power is given by this equation. This is based on the work of Moritz von Jacobi. Essentially, it states that in order for maximum power to be transferred from the source to the load resistance must match the source resistance. Okay. This, as I have stated earlier, also known as the maximum power transfer theorem. It's related to that. Law of max power is his work, and then of course we had maximum power transfer theorem. As an example, not an example, sorry. Maximum power does not mean maximum efficiency. Okay. Two different things. Maximum power does not equal maximum efficiency. As a real life example, let's say you have a electric vehicle. Okay, it has a battery source that's finite energy, and we can run it at different speeds. So you're trying to get from point A to point B. If you want to go or reach from point A to point B in the shortest possible time, on a floor, pull as much energy out from the battery as much as you can, transfer it to the DC motors, speed down the road, get there as quickly as you want. Obviously, it's going to burn a lot, not burn, it's going to use up a lot of the energy, right? every time electrical energy is used for any purpose, there's a conversion that takes place. Conversion always results in loss of that energy, right? You want electrical energy to perform some sort of function, whether it's optical, mechanical, thermal, there's always losses of that energy during that process, during the transfer process. So we can either have maximum power transferred, you can use up all of that energy in a short period of time, or if you want maximum efficiency, then you minimize the amount of losses that take place. So in that electric vehicle, if you want to save on the energy of your battery, then you go at a certain speed. Does not mean you go very slow. There is a fine line between getting maximum efficiency and maximum power. Okay, so efficiency in this case would allow you to go the farthest possible distance on a single charge. That would be efficiency. In regular gas-powered vehicles or fossil fuel-powered vehicles, we would call that as mileage, right? So same principle. Takeaway is maximum power does not equal maximum efficiency. It does not happen. All right. So here we have a graph shows us the IV characteristic of a linear power limited source. We have 4 quadrants in here. Let's say we have a device, a sealed box device. We don't know what that device is or what it does, but at the output of that device is a voltage V, and the current that's flowing is I. So this graph shows us the function of, graph shows us the voltage as a function of the current I. Here is the first quadrant. Here is the second, third, and the fourth. Okay. In the first quadrant, both voltage and current are positive. In the third quadrant, both voltage and current are negative. So in both quadrants, first and the third, if we determine the power associated with that device, it's going to turn out to be positive. Power is equal to V times I. You get plus positive power in the first quadrant. You also get positive in the third quadrant. So if it's positive, that means it's receiving energy, it's receiving the power. That means the device is more likely than not a resistor, passive component. However, in quadrants 2 and in 4, power is negative. Power is negative. P equals minus VI. When power is negative, it simply illustrates in mathematical terms that the source is supplying energy. It is supplying power. And we put a minus sign in front of it. We say it's negative, right? Again, going back to that same point, power, energy, voltage, current are never positive or negative. It's just us humans who put a positive or negative sign so that we are able to balance out our equations. Okay. So if it's a source, that source's behavior is exactly opposite to that of a resistor. The resistor receives energy, source is going to supply energy. Okay. The current that flows in that circuit related by Ohm's law, Vs over Rs. Now, if we have a resistor Rs, its characteristic passes through the origin, 0, 0. It's a passive component. So if the voltage across Rs is 0, the current flowing through Rs is also 0. If voltage increases, current increases. If voltage decreases, current decreases, and vice versa. V equals IR, right? So V is directly proportional to I. A voltage source can be said to have a very similar characteristic to a resistor. Okay. Except now we can say that Vs, which is the constant source, is shifting that IV curve upwards by amount of Vs. And it follows the exact same linear curve. Okay, linear curve. Let's see, how much time do we have left? 2:53. Okay, and this, of course, is for an ideal source. Okay, so the curve for that source is shifted up by the amount of Vs. And of course, we also talked about how an electrical source can be modeled as a voltage source or a current source. Voltage source has a resistor in series, current source has a resistor in parallel. They would have the same VI characteristic as long as this equation holds true. Okay, as long as this equation holds true. So if you have two sources, one is a voltage, the other one's current, as long as this equation holds true, then they are both equivalent to each other. And in the next slide, we'll prove how they are equivalent to each other. Okay. All right. Okay, so let's first take the example of the current. Okay, so we have voltage source Vs, series with a resistor Rs, and we short out the two terminals of that source. If we short out the two terminals of the source, what happens? We are shorting out simply, this SC stands for short circuit, OC stands for open circuit. Okay, SC is short circuit, OC is open circuit. Short circuit simply means you're connecting a wire between those two terminals. So if there's a wire, there's now a pathway for the current to flow. So if current is flowing, we can apply Ohm's law, and we can state I is equal to Vs over Rs, right? I is equal to Vs over Rs. On the other side, if we have a current source in parallel with a resistance, when you short it out, what happens? This current has a pathway to go through here. The short circuit has a resistance of 0. That means all of the current is going down that pathway. Nothing will go through Rs. And hence, this current flowing through IR is equal to 0. If that's equal to 0, then the total current I available at the output terminals is Vs over Rs. Okay. Thus, we can say both circuits are equivalent to each other. Okay. And then let's look at the open circuit. If you keep the terminals of the voltage source open, and we measure the voltage at the output terminals, what do we see? We see that V is equal to Vs. And the reason is, if it's open circuit, there's no pathway for the current to flow through. There's no current flowing through. The voltage drop across that resistor is equal to 0. If the voltage drop across that resistor is 0, it means that both ends of that resistor have the exact same electrical potential. I'll repeat. If we have an open circuit, any open circuit in any network, if you have a resistor that's left hanging and open, there is no current flowing through that resistor. Because there is no current flowing through that resistor, the voltage drop across that resistor is equal to 0. The only way a voltage across a resistor is equal to 0 is if both ends of the resistor are at the exact same electrical potential. So if you have Vs at one end of the resistor, then you have Vs also at the other end of the resistor. And the mathematical proof is right here. If you apply KVL around the loop, you have voltage V, you have voltage Vs, and you have Rs. Voltage V would be equal to the source voltage Vs minus I times Rs. And because I is equal to 0, this term effectively is 0 volts. And hence V equals Vs. This is again an important concept in circuit analysis. There will often be times where during circuit analysis, you may modify circuits, or you will modify circuits to find some quantity. And when you modify circuits, you might place a short or you might open up something. If you open circuit something, that changes things. If you short circuit something, also changes things. To keep that concept in mind. And then lastly, we have this where you have a current source. We are saying Vs over Rs is equivalent to Is. So if we do that, it has no place else to go except through Rs. So if it flows through Rs, we apply Ohm's law, calculate V. V is equal to Vs, sorry, not there, which is still the same as what we obtain for the voltage source. And thus, both these circuits are equivalent to each other. A voltage source in series with a resistor and a current source in parallel with a resistor are equivalent to each other. And because they are equivalent to each other, we can use a technique known as source transformation to go from a voltage source to a current source and vice versa. Okay. So it's 3 o'clock. We had to go by a little bit faster, but we'll end class here today and we'll pick up here again on Wednesday.